Preparing for a quantum software engineer interview. You've reached Candy Mentor, and this video is for you. We'll walk through 15 key questions you're likely to face. For each question, you'll see a sample answer, followed by the key points to cover. Subscribe, like, and share. And drop a topic request in the comments. Question 1. How is a qubit different from a classical bit, and why is superposition often misunderstood? A qubit is a two-level quantum state represented as alpha 0 plus beta Lx1, where amplitudes are complex and measurement returns one classical outcome with probabilities alpha squared and beta squared. Superposition is not magic parallel brute force. Algorithms gain power by shaping amplitudes through interference. In interviews, I emphasize normalization, phase, measurement collapse, and the fact that useful quantum programs amplify correct answers while suppressing wrong ones, as in Grover's search or phase estimation. While answering, focus on state representation, amplitudes, normalization, measurement probabilities, phase, and why quantum advantage comes from interference, rather than simply evaluating every possibility in parallel. Question 2. What does it mean for quantum gates to be unitary, and how do gates like H, X, and CNOT behave? Quantum gates are unitary operations, so they preserve norm and are reversible. X flips a qubit. H creates phase-sensitive superposition, and CNOT entangles a control with a target. Unlike classical AND or OR, a gate cannot erase information unless measurement or reset is involved. When coding circuits, I think in matrices for correctness, then in gate decompositions for hardware constraints, because real devices support only limited native gate sets. Make sure to cover reversibility, matrix representation, norm preservation, common single qubit gates, controlled operations, entanglement creation, and the difference between logical gates and hardware native gates. Question 3. How would you explain entanglement to an engineer? And where does it show up in quantum software? Entanglement is correlation that cannot be explained by independent qubit states. A Bell pair, created with H then CNOT, measures as 0, 0 or 1, 1 with equal probability, but not because the values were pre-written. The joint state carries the information. In software, this matters for teleportation, superdense coding, and algorithmic speedups. I avoid saying it enables faster-than-light communication. Measurement outcomes are random, and classical communication is still required. In your answer, talk about non-separable joint states, Bell pairs, measurement correlations, no faster-than-light signaling, and practical uses such as teleportation, protocols, and algorithmic primitives. Question 4. What happens during measurement, and why does the no-cloning theorem matter for debugging quantum programs? Measurement converts a quantum state into classical data in a chosen basis, and changes the state according to the observed outcome. That is why debugging quantum programs is different from printing variables mid-execution. You cannot copy an unknown state either, because no cloning follows from linearity. Practically, I delay measurement until needed, use basis rotations to measure X or Y observables, and treat readout results statistically, not deterministically. Be sure to mention basis-dependent measurement, probabilistic outcomes, state collapse, statistical interpretation, no cloning, and how these constraints change debugging, logging, and intermediate inspection strategies. Question 5. How would you create and verify a Bell state using a framework like Qiskit or Cirq? For a Bell state, I apply H to qubit 0 and CNOT from qubit 0 to qubit 1. In pseudocode, H0, CX01, measure both. The ideal counts are roughly half 0, 0 and half 1, 1. In Qiskit, I would build a quantum circuit, add classical bits, execute on a simulator first, then compare hardware counts with expected correlations. The key is verifying correlation, not a specific single-shot result. Question 6. When would you use a quantum simulator instead of real quantum hardware? State vector simulators are exact for small systems, but scale exponentially in memory, about 2 to the power of n complex amplitudes. Hardware gives real noise, connectivity limits, calibration drift, and Q latency. I use simulators to validate circuit logic and expected distributions, then run small hardware experiments to estimate practical behavior. A good answer mentions shot noise, seed control, tensor network alternatives, and why a 40-qubit circuit may be impossible to simulate, but still noisy on hardware. Make sure to discuss state vector simulation, exponential memory scaling, tensor network methods, noisy simulators, real device calibration, queue times, shot noise, and validating logic before hardware execution. Question 7. What is circuit transpilation, and why can it change the performance of a quantum program? Transpilation maps a logical circuit onto a specific device. It decomposes gates into the backend's native gate set, inserts swaps to satisfy qubit connectivity, and may optimize depth or error exposure. I watch the resulting circuit, not just the source code, because added swaps can dominate runtime. In practice, I choose initial layouts, compare optimization levels, and balance fewer gates against using higher fidelity qubits or shorter coherence paths. In your answer, focus on mapping logical circuits to hardware topology, native gate decomposition, swap insertion, circuit depth, fidelity, optimization levels, and backend-specific constraints. Question 8. How do noise and decoherence affect quantum programs, and what mitigation techniques would you use? Noise is unavoidable on NISQ devices, so I model it instead of pretending circuits are ideal. Common channels include depolarizing noise, amplitude damping, dephasing, and measurement error. For mitigation, I might calibrate readout matrices, use zero-noise extrapolation, reduce circuit depth, or exploit symmetry checks. The trade-off is extra shots and assumptions. Mitigation improves estimates, but does not create fault-tolerant computation. I always report confidence intervals with mitigated values. Be sure to mention NISQ limitations, common noise channels, T1 and T2 effects, readout error, circuit depth reduction, zero-noise extrapolation, measurement mitigation, and trade-offs. Question 9. What is the difference between quantum error correction and quantum error mitigation? Quantum error correction protects logical qubits by encoding them into many physical qubits and repeatedly measuring syndromes without directly measuring the data. Error mitigation is lighter. It post-processes or reshapes noisy experiments. Surface codes are popular because they use local checks and have thresholds, but the overhead is huge. In interviews, I separate correcting errors during computation from estimating cleaner expectation values after noisy runs today. While answering, distinguish logical qubits, physical qubits, syndrome measurements, surface codes, thresholds, overhead, post-processing methods, and why mitigation is common on near-term devices. Question 10. Explain Grover's algorithm and the practical limitations of implementing it. Grover's algorithm gives a quadratic speedup for unstructured search, reducing O of n oracle queries to O of the square root of n. The implementation alternates an oracle that flips the phase of valid states with a diffusion operator that amplifies them. I would not oversell it. Building the oracle can be expensive, and the result is probabilistic. It is strongest when the predicate is cheap, reversible, and classical brute force dominates cost. Make sure to cover unstructured search, oracle design, amplitude amplification, diffusion operator, quadratic speedup, probabilistic measurement, reversible predicate implementation, and why oracle cost matters. Question 11. What role do the Quantum Fourier Transform and phase estimation play in quantum algorithms? Quantum phase estimation estimates an eigenvalue phase of a unitary and is a core primitive behind Shor's algorithm and many chemistry methods. It uses controlled powers of the unitary plus an inverse QFT to extract phase bits. The catch is resources. Deep controlled operations and fault tolerance are usually required. On NISQ hardware, iterative or variational alternatives are often more realistic than textbook phase estimation. In your answer, talk about QFT as a basis transform, phase kickback, controlled unitaries, inverse QFT, Shor's algorithm, chemistry applications, and resource requirements. Question 12. How would you implement a variational quantum eigensolver for a molecular chemistry problem? VQE is a hybrid algorithm for estimating ground state energies. The quantum processor prepares a parameterized ansatz and measures Hamiltonian expectation values. The classical optimizer updates parameters. For a molecule, I map fermionic operators to qubits using Jordan-Wigner or Bravi-Kitaev, choose an ansatz, group commuting measurements, and minimize energy. The engineering challenge is shot cost, barren plateaus, optimizer noise, and choosing an ansatz expressive enough without making circuits too deep. Be sure to mention Hamiltonian construction, fermion to qubit mappings, ansatz selection, parameterized circuits, expectation measurement, classical optimization, shot cost, barren plateaus, and convergence validation. Question 13. How does QAOA work for a problem like MaxQut, and how would you evaluate its results? QAOA targets combinatorial optimization by alternating cost and mixer Hamiltonians. For MaxQut, I encode edges into phase separators and use X rotations as mixers, then optimize angles classically. Increasing depth P can improve solution quality, but increases noise and optimization difficulty. I would benchmark against strong classical heuristics, not only exact solvers, because practical value depends on approximation ratio, runtime, and hardware feasibility on current devices. While answering, focus on cost Hamiltonians, mixer Hamiltonians, parameter depth, classical optimization loop, approximation ratio, benchmarking against heuristics, hardware noise, and scalability limits. Question 14. How do you test and debug quantum software when outputs are probabilistic? I test quantum software at multiple levels. For small circuits, I compare state vectors or unitaries against hand-derived expectations. For larger circuits, I test invariance, normalization, conserved symmetries, expected measurement correlations, and regression distributions with statistical tolerances. I also seed simulators, isolate oracle logic, and inspect transpiled circuits. The mistake is expecting exact counts. Tests need confidence intervals, because quantum output and hardware noise are inherently statistical. Make sure to cover simulator tests, state vector comparison, unitary checks, statistical assertions, confidence intervals, seeded runs, invariant testing, transpiled circuit inspection, and hardware regression baselines. Question 15. How would you design a cloud service that submits, tracks, and reproduces quantum computing jobs? I would build the service as a workload orchestrator, not just a thin SDK wrapper. Users submit circuit, backend preferences, shot budget, and metadata. The service validates, transpiles, estimates cost, queues jobs, and stores results reproducibly. I would track backend calibration, circuit hash, transpiler version, random seeds, and error mitigation settings. Reliability comes from idempotent job submission, retries around provider failures, observability, and clear separation between simulation and hardware execution. In your answer, discuss API design, circuit validation, backend selection, transpilation metadata, job queues, idempotency, retries, result storage, calibration snapshots, observability, cost controls, and reproducibility. If you are still with us, congratulations. You are much ahead of the rest and serious about preparing for your interview. We hope we were able to add value to your preparation and create some helpful content. Do not forget to like and share this video. Your small act can do great things for us.